Okay, another nice thing that can be explained with our new model is the transition metals. So transition metals all seem to have these common properties. And the common properties they all have is that they tend to form charges. A lot of them form a +2 charge, not all, but most. And they behave a lot like a metal. Our new model for the atom will help us understand why that is. Let's start with calcium. And we'll work our way from calcium all the way over to zinc. And we'll see, using an energy level diagram, why all of these atoms would have some pretty similar chemical properties. So, with our energy level diagram, starting with calcium, which has an atomic number of 20, I can have my 1s electrons, 1, 2, my 2s electrons, 2, 3, 4, my 2p, getting me up to 10, my 3s, I'm at 12, my 3p, I'm at 18, and for calcium, my 4s, 2 more, that's my 20. Now, let's think about this atom, and let's remember the concept of shielding. Shielding says to outer electrons, inner electrons and protons, inner electrons and protons appear as one overall charge, and that charge I call the effective nuclear charge. If you're a little hazy on this concept, if you go back and search through my other videos for effective nuclear charge, I talk about this a lot more in previous videos, so I'm not going to get into it here. But the idea is that all of these, since I have 4 s electrons, all of these inner electrons, of which there are 18, will cancel with the inner protons, of which there are 20, and leave me with an effective nuclear charge of +2. This effective nuclear charge is a representation of how attractive the atom is to bonding electrons. So, with calcium here, we'd have an effective nuclear charge of +2. And that would be holding on to these electrons. Effective nuclear charge ranges from +1 to +8. So +2 is pretty low, which is why calcium would react by losing those 2 electrons and forming its charge of +2. Let's look at what happens when we go from calcium, and we're going to go now to scandium, the next guy over. So our atomic number is going from 20 to 21. What that means then is now for scandium, I'm going to have 21 protons, and I have another electron to work with. But that next electron is going to go up into these 3D shells. What's interesting or different about this is that even though these shells are higher energy, they're still smaller. And that means they're still able to engage in shielding. So while I added one more proton, I actually also added one more electron to my overall shielding amount. I still have my 2, 4, 10, 12, 18, but now this 19th electron can also engage in that shielding. What that means then is my effective nuclear charge is stuck at +2. So when this atom is considering what it's going to do to bond, it still has 2 electrons that are fairly available to be given away, so it's still behaving as a metal, and it's still behaving as a metal that wants to form the charge +2. So despite the fact that I added a proton, I also added an inner electron, And as a result, from a chemical reactivity standpoint, scandium is essentially the same as calcium. As I go across, I can add more and more and more electrons up here. If I added 5, for example, I would be at manganese. But my proton number would go up at the same time. So now I'd be up to a proton number of 25 and an electron number of 23, and I'd still be sitting at an effective nuclear charge of +2 with 2 possible electrons to give away. So I can go all the way across the transition metals, but because I'm adding protons and inner electrons from a chemical reactivity standpoint, the two additional species cancel each other out, and the overall properties of the atom remain roughly the same. Now, these electrons that are going into these shells offer these atoms a little bit of flexibility, and that leads to some of the multivalent things that we're going to see with the transition metals. Also, while we say they're shielded, remember shielding is an idea, it's not perfect. And so as we shield these atoms, their properties will change slightly, but this is the reason why the transition metals as a whole have a fairly common reactivity or chemical properties.